Okay, so let's get underway. We were talking about spin a half, the most important type of spin, yesterday, and we got this far. So any state, as regards its spin, its orientation, should be expandable as a linear combination of the state plus, which means you are certain to get a plus a half if you measure the spin along the z-axis, and minus, and there will be some coefficients. There will be these coefficients here, and a complex number here, and a complex number there. The amplitude to measure plus a half on Sz, or the amplitude to measure minus a half on Sz. And we're calling these, it's obviously handier notation to call that thing A and this thing B. And then what we want to be able to do is write the result of using some spin operator on this arbitrary state of psi. We call that phi. We can also expand as a linear combination of this and this because they're a complete set of states for the orientation of this spin-a-half particle, spin-a-half system. And we, I hope I persuaded you yesterday that these numbers, these amplitudes C and D, can be obtained as the vector on the left. If on the right we put in the two numbers that characterize psi on the right, we get out on the left the two numbers that characterize phi after we've multiplied by this matrix of four complex numbers being the expectation value of the relevant, of whatever operator we're trying to use between the plus states, the minus states, and then these non-classical off-diagonal bits on each side. And we said, I think we finished by saying that if I is Z, in other words, if we're interested in the result of using Sz on psi, then this matrix is very simple because Sz on plus is simply a half of plus. So we get a half appearing here. We get minus a half appearing here because Sz on minus is minus a half times minus. And we get nothing appearing here and here because plus and minus are orthogonal. So we have this diagonal matrix, which is no accident. It is simply the matrix that contains the eigenvalues of Sz down its diagonal because we used as basis vectors the eigenkets of Sz. We made that choice, and the result is that the matrix representing Sz is diagonal with its eigenvalues down the diagonal. And this matrix is conventionally written as a half times this matrix, which is called sigma Z, and is called a Pauli matrix because Wolfgang Pauli introduced it into physics. Although it was known to mathematicians, the matrices like this. Okay, so more interesting is if we ask ourselves, what's the matrix for Sx? So the matrix from Sx is going to involve things, well, we're going to have, for example, plus Sx plus, this is a complex number, we want to know which complex number, and the secret is to write of calculating this, is to write Sx as a half of S plus S minus, where S plus minus are the matrices, are the operators that we already introduced in the context of J and L to reorient the angular momentum either towards the z-axis or away from the z-axis. So these are Sx plus and minus I times Sy, right? So this operator was introduced in the form of J plus minus, but remember spin and total angular momentum have the same commutation relations, the same behavior in every way. So these ladder operators are this, and obviously if you add S plus to S minus, you get 2 Sx because the Sy terms cancel. So this is definitely the case. So this thing here can be written as a half of plus S plus 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 plus, sorry, oh yeah, well this is what I'm trying to calculate, yeah. S plus S minus plus. S plus tries to raise this to an even larger value. This is plus a half. It'll try and raise it to plus 3 halves, but no such value is allowed because the total spin is only a half, so it kills it in the process. So therefore, this one is 0. S minus successfully lowers this to minus, but minus is orthogonal to plus, so this is 0. So this element here is 0. And that's the top left corner of the matrix for Sx is 0. Similarly, exactly the same reasoning would lead you to conclude that the bottom right-hand corner is 0, and the non-zero elements occur off diagonal. So if we look at plus Sx minus, we're looking at a half of plus S plus minus plus plus S minus minus. S plus raises minus to plus successfully. S plus on minus is exactly 1 times plus. So this number here is equal to 1. And minus tries to lower this and kills it in the process. And therefore this is equal to 0. So this element, this off-diagonal element, is in fact equal to a half. We know that the bottom right-hand element is the complex conjugate of the top right-hand element because S is a Hermitian operator. So we know now that the matrix is Sx is represented by the matrix half of nothing, 1, 1, nothing, also known as a half of sigma x, the Pauli matrix. This is the Pauli matrix sigma x. And when we do the same thing to find out what Sy is, we write this as a half of plus, 1 over 2I of S plus minus S minus, right? Because if you take the difference of Sx plus Iy and Sx minus Iy, you will end up with 2I Sy. So we have this, and what do we get? This S plus raises this to minus to plus. So plus S plus minus again equals 1. So therefore, this is equal to 1 over 2I, also known as a half minus I over 2. So the matrix representing Sy is going to be a half of 1 minus I. Sorry, what did I say? 1, nothing. Nothing. The diagonal elements will be nothing for the same reason that they were with X, also known as a half of Pauli's matrix sigma Y. So that's where the Pauli matrices come from. They're simply the matrix representations of the spin operators in a basis. When you choose as your basis the eigenvectors, the eigenkets of sigma z. So let's use these, use this apparatus to do something slightly interesting. It's an excellent exercise, both in practicing getting experimental predictions out of this abstract apparatus, and also we learn something interesting about how the orientation of atomic scale things behave, somewhat counterintuitive arrangements. I don't think this this projection system is going to work today for some reason. So, okay. So the point is that a spinning charged body is a magnetic dipole. I think that's kind of plausible, so that electrons, neutrons, protons, electrons, protons, being spinning charged bodies have little magnetic moments. They are little magnets. So if you put a magnet in a B field, you have, this is the energy of a magnetic dipole in a mag field. So there's a minus sign here which says that the energy is lowest when the dipole is aligned with the magnetic field, right? So when this dot product is positive, the energy is lowest. So that's why magnets, compass needles and whatever, align with the magnetic field. That also means that if a magnetic dipole is aligned with the field, its energy will drop as it moves into a region of bigger field, because this will become a more negative number. Whereas if it's anti-aligned with a magnetic field, then its energy will increase if it moves into the magnetic field, because this will be negative and the two minuses will cancel. We'll have a more positive energy. So since things tend to move in the direction that minimizes their potential energy, we have that magnets aligned with B will be sucked into a region of stronger B. So a dipole, aligned with B, so that means that mu dot B greater than naught is sucked into a field. So if the field strength varies spatially, which it often does, the particles which have their fields, their dipoles aligned will be sucked into B, and similarly the other ones will be repelled. So the anti-aligned, aligned dipoles will be repelled from a region of high B. So that was the physics that Stern and Gerlach exploited in 1922 in experiments which astounded the world. They made themselves a magnet, or should we call this north, and we'll call this south. They made themselves a magnet which had pole pieces, one of which was pointy and the other of which was flat, or even, I think it was flat. But it could also be concave like this. And then you can imagine how the field lines run. The field lines run like this somehow. I'm not doing a very good job of it. My diagrams are usually rather rubbish. The point is that here we have a crowding of field lines, which means we have high B near knife edge. So I have a nice picture of this, but the computer isn't willing to show it because this is the end view of a long thing. So this is like the point of a knife, right? We're looking end on a point of a knife, and this is a table somehow. So if you have some particles with some spin coming in here and aim it right so that they're heading for this, they're heading a bit below this region of high magnetic field, like this, then the ones that have their spin aligned this way into B are going to be sucked into the region attracted by the region of high B near the point of the knife, and move on up here. So this is the particles which have mu dot B greater than naught, and particles with anti-aligned with mu dot B less than naught will come down here. Of course, these are all grotesquely exaggerated. In fact, you'll have a very subtle curvature, and then you'll have a straight line. Right. So we get the particles deflected either way. So if you have, so what they did was they took silver atoms, because silver atoms turn out to be spin-1/2 particles, coming in here. And they found, which surprised them and everybody else, that half of their silver atoms went off this way, and half of their silver atoms went off that way. So when they detected the atoms on a screen over here, they got two blobs distinctly separated. The quantum mechanical interpretation of this is that as these atoms, when the atoms are in here, they, sorry, I haven't said that mu, the magnetic moment, is equal to some number, the gyromagnetic ratio, times the spin operator. So when they're in here, they're, the magnetic field is, as it were, measuring their component of spin in the direction of the magnetic field. That's what you say to yourself. So, and there are only two answers possible. Either you'll get plus a half or you'll get minus a half for the value of this. And therefore, mu will be either a half g in the direction of B, or it'll be minus a half g in the direction of B. If it's so, and the half for which it's plus a half g will be deflected that way, and the other lot will be deflected down here, and there you go. So at the end of the day, you have a Stern-Gerlach filter. You put in the particles with. They've just come out of some oven. You've made the silver. You've heated up some silver in an oven, made some silver vapor, allowed it to diffuse out of some holes, collimating slits, and that kind of stuff. So it's coming along here with some thermal velocities. And out of your filter, you have a load of you have atoms which have their spins, in this case, up on Z, and the ones that come out here are in this state. So it's a machine it's a practical device for creating silver atoms which are in this state. And now you can play some entertaining games by installing another Stern-Gerlach filter. So let's just block these off, stop them being a nuisance. Stick in another Stern-Gerlach filter here. And now let's measure the let's measure S sub n. So let's measure the spin along some unit vector n, and let's take, so we're going to have this to be the x direction, we're going to have this to be the z direction, and what the y direction will have to be out of the board, all right? And what we're going to do is we're going to take n is equal to nothing, comma, sine theta, comma, cos theta. So n is going to be a vector, which if theta is nothing is just in the z direction, and if theta is pi by 2, it's in the y direction, and it can be allowed to scan between these directions as we vary theta. And what we want to do is calculate which fraction of the atoms will survive, will get through the second filter. So this is the filter F1, this is the filter F2, and you want to calculate the probability that an atom gets through both filters. Or let's focus for the moment on the probability that an atom that has got through the first filter gets through the second filter. So the probability that you pass F2, given that you passed F1 in quantum mechanical language, is plus a half on n, given that you're, well, we'll just say plus on n, given that you were plus on z. So this is the state that you're in. Up there it's just called plus, but now I put in a z to distinguish it from this, which is in the direction of n, that this is an eigenket of Sz with eigenvalue a half. This is an eigenket of S sub n with eigenvalue a half. And this pair of things makes me the amplitude, by the basic dogma of the subject, for the probability of this outcome. So I need to mod square this, and I've got the probability that I want. So we can work this out. We can get this complex number as soon as we know how to write plus on n as an amount of plus on z plus an amount of minus on z, right? Because, so if we get this number and this number, then we have that the probability that we want is going to be mod A squared, because A star is going to be exactly that number. Right? To get out of this ket, you could get the bra you want up there by complex conjugating it. You'd have an A star, bang in with plus on Z, and you pick out A star. So the probability we want is just mod A squared. So that's our exercise to find A and B, and we'll be all done. How to find A and B? Well, what's the defining characteristic of that ket? It is that it is an eigenket of this operator with eigenvalue a half. This defines n. And it's totally characteristic of these sorts of calculations, of a wide range of quantum mechanical calculations, that this sequence of arguments, I want a certain complex number, it will involve some ket. Ask yourself, what is the defining characteristic of the ket? It will usually be because it is an eigenket of some operator. Now we have a well-defined mathematical problem. Find it, because what is Sn? Sn is equal to a half of nx sigma x plus ny sigma y plus nz sigma z. Sort of a dot product between the unit vector n and the vector made up of the three Pauli matrices. Well, nx is 0, so basically we've got an ny we agreed was going to be sine theta, and this we agreed was going to be cos theta. So at the end of the day, it is a half of now, sigma z, we've got up there, it's got 1 in the top left-hand corner and minus 1 in the bottom, so I get a cos theta and a minus cos theta appearing on the diagonal because of sigma z. And this has got a minus I in the top right-hand corner, so we get a minus I sine theta appearing there, and its complex conjugate has to appear down here. So this is the matrix that represents Sn, where theta is defining the direction of n. And now all we have to do is say that this matrix, cos theta minus I, sine theta I, sine theta cos theta on AB is equal to AB. This eigenket, this vector has to be an eigenket of this matrix with eigenvalue 1 in order that it's an eigenket of Sn with eigenvalue a half, right? Because the original expression was Sn on this equals a half of that, but here is a half. I can cancel on the two sides. So I'm looking for the eigenket of this operator with eigenvalue 1. Notice I don't waste my time finding out what the eigenvalues of this operator are, of this matrix are. I know that because this is a matrix that represents a spin operator, Sn, I know before I start that the eigenvalues are plus and minus, of this one, plus and minus a half, of this one, plus and minus 1. So we don't waste time finding out what the eigenvalues are. We just get on and solve these equations. There are two equations here, but because we're looking at an eigenvalue problem, only one of them, these two equations are linearly dependent upon one another. Only one of them contains useful information. The other one repeats that information. So we merely need to look at the top equation, and it says that A minus 1, A times brackets 1 minus cos theta. So if I'm going to get A cos theta equals A on the right-hand side. So if I go on the right-hand side, we'll have A cos theta, A into 1 minus cos theta is equal to minus I B sine theta. In other words, we're going to have that B over A, which is all that I can, it's only the ratio of A to B that I can determine out of this. The absolute values have to be determined from a normalization condition, are equal to B over A is equal to 1 minus cos theta over minus I sine theta. And we can clean this up a bit if we use some half-angle formulae, because this on the top is twice the sine squared of theta over 2. sine theta is twice sine theta upon 2 cos theta upon 2. So we can cancel a number of things. The 2's cancel, one of the sine thetas cancel, and we end up with sine theta over 2 over minus I cos theta over 2. So I can write now that AB is equal to cos theta over 2 I sine theta over 2. So if you work out the ratio B over A of these two, I think you will get that, because this minus I could be put as an I on the top. And moreover, this thing is correctly normalized. It just happens. So in principle, I would now need to deal with the normalization. I've only been calculating the ratio of the components. I want mod A squared plus mod B squared to come to 1, but it jolly well does by good fortune, right? So this is the complete bottom line. This gives you okay, right. So the probability that we pass F2, given that we passed F1, is actually equal to, we said it was going to be mod A squared, is therefore cos squared theta upon 2. Does that make sense? If theta is equal to nothing, then the second filter is also measuring the z component of angular momentum. And the output from the first filter is guaranteed to return plus a half for the z component of angular momentum. So this probability must be 1, and indeed cos squared of nothing is 1. If the theta is pi, then the second one is plus a half, then n is pointing in the minus z direction. So getting plus a half in the direction n is equivalent to getting minus a half in the direction z. But we know for certain that we're going to get plus a half in the direction z, so the probability of this happening is 0. And indeed, cos squared of, if I put theta equal to pi, I'm looking at cos squared pi upon 2, which is nothing. So that makes sense. If I put theta equal to pi upon 2, then we're measuring, then the n direction becomes the y direction, and we're measuring in a direction which is orthogonal to the z direction. And then you would think that knowing what component of the angular momentum in the z direction was couldn't possibly affect the angular momentum in the y direction. So you would expect that there was equal probability that half the probability of passing the second filter, that is to say, of getting plus a half for the spin along y, that plus a half on y and minus a half on y be equally likely by the symmetry of the situation. And indeed, cos squared of pi upon 4, or cos of pi upon 4 is 1 upon root 2, to cos squared of pi upon 4 is a half, and that makes perfect sense as well. So this formula predicts the kind of thing that you would expect. Okay, suppose we now have we won't do this in all detail, but let's just sketch it out. Suppose we have now another filter. So we have F1 as before. We have F2 as we've just calculated. Now suppose on the output of F2 we include F3. Right. So this one is going to measure in the theta direction, as said. This one, let's say this one has its axis in the phi direction, also in the xy plane, right? So you measure, first of all, the spin on z, then you measure on the unit vector cos theta, nothing, sine theta, cos theta, sorry. Then you measure, and then those that return plus a half in that direction, you measure in the direction nothing, sine theta, sine phi, cos phi. Suppose we do that. So the probability of passing F3, given that you passed F2, is going to be we'll call this vector n, and we'll call this vector m, say. No, we'll use this notation. This will be a half on phi, a half on theta. So the output from this filter definitely has particles with plus a half component of angular momentum in the direction defined by theta, and I want to know the amplitude that those particles will definitely give me a plus a half if I measure in the direction defined by phi. The answer to that is, according to the dogma of the theory, it's that. And I can expand that into here. I can slide the identity operator, taking the form of plus on z, plus on z, plus minus on z, minus on z. We've slid identity operators in many times before in more complicated contexts. So this thing that we're doing here is going to be a half phi, sorry, that's a blunt end, a half phi plus z, a half theta, plus a half phi minus z, a half theta. Now these complex numbers we already know, we just calculated them, right? This was A, which we used. This was B, which we didn't use, but we got it written down up there. It's I sine theta upon 2. So this one here is cos theta on 2. This one here is I sine theta over 2. But we also know what this is, because this is going to be the same excuse me, we have a complex. Let's just ask ourselves carefully exactly what is B. B is actually the complex conjugate of this. Sorry. These need complex conjugate signs. Can we remind ourselves actually where we are on this? I'm now worried about whether I'm dealing with a complex. Some of these need complex conjugate signs. What exactly are A and B? They were defined. Okay, just to get this right. What we said was that a half on theta was equal to A plus Z plus B minus Z. That's what we said. That was the definition of A and B. So what is this? This thing here is plus on Z, a half on theta. Yeah. So what I said originally was correct. There are no stars here. Okay. So that's just for note. All right, now, back to this. This is, the complex conjugate of this is essentially the same as that, with theta replaced by phi. So we know that this will be the complex conjugate of this with theta replaced by phi. This is in fact real, so this is going to be cos phi over 2. Similarly, this, the complex conjugate of this, is the same as that with theta replaced by phi. So I now have to write down the complex conjugate of that, which is minus I sine phi over 2. So that's what that comes to. So the probability that we get through F3, given that we got through F2, is going to be cos squared phi over 2 plus, because that minus sign and that I and the pair of i's make a plus sign, sine squared theta at phi. Which is also known as cos phi over 2 minus theta over 2. I think, if by trig formulae. So does this make sense? It tells me that I will, if phi over 2, if phi is the same as theta, I'm certain to get through. That's good. If the difference in the angles is pi upon 2, then I have a chance. We have failed to mod square the whole thing. That's what's gone wrong. Maybe there's muttering about that. So this got expanded to this, and this whole thing needed a mod square. And this needed a mod square. And we were doing various calculations, and then this needed a mod square, and this needed a mod square, so it just became cos squared. Right. So when the angle is, so all this tells us is that, it had to tell us, we would have been worried if we hadn't discovered this, that the probability of getting through the third filter, given that we got through the second filter, should depend only on the difference in the two angles, and indeed should go like the difference divided by 2.
Professor,
yep.
How exactly did cos phi over 2 cos theta over 2 become cos squared phi over 2?
Oh, gosh, yeah, sorry. You're completely right. Right. So let's go back to this line here. This was cos phi over 2, cos theta over 2, plus sine phi over 2, sine theta over 2. That's what it is, and then we have to do a mod square of it. Yeah, excuse me. And we have a formula in trig, right, which says that this combination of cosines and sines is the cosine. What's in here is actually the cos of phi upon 2 minus theta upon 2. And then we had to square it. Sorry. Okay. Now we can learn something. We can make a little get a little physical result here by considering the case that theta is equal to pi on 2, phi is equal to pi. What does that mean? That means that n is equal to e sub y. The axis of the second filter is equal to e sub y. You're measuring the spin in the y direction. The axis of this one, we'll call it m, is then equal to minus ez. So what's the probability of passing F3 given that you passed F1? And that's the same as the probability, what that is physically, is the probability of eventually having your spin being measured to be in the minus z direction, given that as you emerge from F1, you had your spin in the plus z direction, right? So we already had that this, okay, right. What is that? Well, it's the probability of passing the second filter, given that you passed the first, times the probability of passing the third filter, given that you passed the second. And therefore, it's equal, this probability was a half. In this, we already discussed that. In the case that theta was pi upon 2, so we were measuring in a perpendicular direction to the direction associated with the first filter, this probability came out to be a half. We felt that was natural. This probability is going to be a half as well, because we've seen that it depends on the difference in the two angles, and the difference in the two angles here is pi upon 2, so it's times a half. So it's a quarter. So a quarter of the particles which emerge with their spin, quote unquote, in the z direction, are found eventually to have their spin in the minus z direction. And this is concrete evidence that the second filter hasn't just measured the spin of the particle, it's changed the spin of the particle. It's redirected it. So this is a manifestation. This result is a manifestation. If we had, so the probability of just doing F3 given F1 and no second filter is 0. So putting in the second filter, the intermediate filter, affects the result, and that's the realignment. So we should talk briefly, as I say, spin a half is far and away the most important case, but let's just briefly talk about spin 1 and make the point that everything that we've been doing here generalizes to arbitrary spin. There's nothing we've been doing here which is really peculiar to spin a half. So in the case of spin 1, we have that psi can be written as an amount of 1, so 1, 1 if you like, plus an amount of 1, nothing, plus an amount of 1 minus 1. So there are 3 complex numbers needed to define the orientation of the spin of a spin 1 particle. And for example, a W boson or a Z boson are particles with spin 1. Photons also have spin 1, but they have certain pathologies because they have 0 rest mass. So it's as well not to include them in this discussion. So we have that. The consequence of that is that if I have a spin operator, SI, working on psi, that maps to a matrix problem where we write this as ABCD times 1, 1 plus E times 1, nothing plus F times 1 minus 1, right? So this is represented by 3 complex numbers, D, E, and F. This is represented by A, B, and C, and there will be a matrix relation between these. We will have that D, E, and F are equal to a matrix, which we will make with plus, we will have 1, 1. Let's leave off the total angular momentum quantum numbers. So let's just call it 1, SI, 1, and then we'll have 1, SI, nothing, and then we'll have 1, SI, minus 1, and so on and so forth. And here we will have nothing, SI, 1, nothing, SI, nothing. So we have a 3 by 3 matrix operating on A, B, C. This is how we will concretely do our computations. And we need to know, so we'll have 3 matrices, one for Sx, one for Sy, and one for Sz. Sz will be the easy one to do. Sz will be the matrix of its eigenvalues down the diagonal. So that'll be 1, nothing, minus 1, and nothing everywhere else. Which follows immediately from the fact that Sz on this produces 1 times this, etc., etc., etc. And when we want to work out what to do for Sx, so when we want to work out 1 Sx1, we'll replace that Sx by a half S plus S minus. S plus will kill this. S minus will lower this to nothing, which is orthogonal to this, so we'll have a naught in this slot. When we put Sx in here, we have a half of plus minus. Minus will lower this to minus 1, which is orthogonal, but plus will raise it to this, and it will produce, in fact, root 2. We'll have that S plus operating on nothing will turn out to be root 2 times 1. So Sx will be a half of nothing, root 2, nothing. We'll get nothing in the right thing because S plus can raise minus 1 to nothing, but it can't drag it all the way up to 1. And S minus, of course, kills minus 1. So we get a matrix that looks like this. And we will get for Sy a matrix that's most handily written as 1 over root 2. This is more easily written as 1 over root 2 of nothing, 1, nothing, 1, nothing, 1, nothing, 1, nothing. Just taking out the factor of root 2. And this one is most easily written, is handily written just the same way we derive it. Nothing, minus I, nothing, minus I. It's a Hermitian matrix, so here goes I, nothing, nothing, nothing. So these are the generalizations of the Pauli matrices for a spin 1 problem. And it's worth doing some Stern-Gerlach type experiments, thought experiments, with these spin 1 systems to just see what the differences are. I did want to talk about let's just briefly talk about this. Let's go all the way to spin S, which is much greater than 1, right? So in the classical regime, we want to understand how out of this can we recover the classical situation that if I hold up a piece of chalk, it has a well-defined orientation, none of this probabilistic, this thing and that thing and the other thing. You can see where the damn thing points, right? We have to recover this out of this probabilistic apparatus. And the way to do that is to imagine what these spin matrices look like for spin n. It's absolutely straightforward to construct them. Everything we've done carries over absolutely straightforwardly. We have that Sn, for Sz in this case is going to be S minus 1, S minus 2, down to minus S along the diagonal. It's going to be the matrix of the eigenvalues of Sz and diagonal. Sx is going to be, here we will have the state S, S, X, S. Then here we will have S, Sx, S minus 1, and so on. S, Sx, S minus 2. If you want to apply this in classical physics, this matrix will be on the order of 10 to the 30-something by 10 to the 30-something. Right? It'll be enormous. But nearly all the numbers will vanish because, well, this number we already know is equal to 0. This number vanishes because this you replace by a half of S plus S minus. S plus kills this. S minus lowers it to something orthogonal to this. This will be non-zero because S plus will raise that to S, which will couple to that. And in fact, this will turn out to be alpha of S minus 1. So when Sx works on this, we get a horrible square root, which I'm calling alpha of S minus 1 times S. So that's what this will come to. This will come to nothing because we'll have S plus that'll raise this to S minus 1, which is not good enough. And S minus will lower it, which is useless. So this is equal to 0, and everything else is going to be equal to 0. So this matrix is going to consist of a line of non-zero numbers just above the diagonal, nothings down the diagonal. So let me write this out. This is going to be, on the diagonal, precisely nothing. Above the diagonal, we will have alpha of S minus 1, which is easily worked out. It's the square root. Here we will have alpha of S minus 2. Here we will have alpha of S minus 3, and so on, down the diagonal. And just below the diagonal, we have the complex conjugates of those. These are, in fact, real numbers, and therefore we have the same numbers. And nothing's everywhere else. So this is a very simple matrix. It just has two non-zero diagonals, and we can work with it. And we can now do things like, suppose we have no time, so it's time to stop. Sorry, but I think it probably is worth just doing this, and I'll finish it off tomorrow. Yep.